Hello. So today we are starting our unit on gases and the gas laws. So of our three states of matter, of course, we have solids, liquids, and gases. Gases are going to be our state of matter that have the highest energy. So some properties of gases that are important for us to know. They're going to assume the volume and the shape of their container. So what exactly does that mean? If we have a gas, let's say in a container this size, and I was able to put the gas into this container, the gas would take on the larger volume and shape of that new container because gases can spread out and take up as much space as they possibly can. Gases also have indefinite volume and indefinite shape. That goes right along with what we just talked about. There is mostly empty space between gas particles. Because they take up the maximum amount of space possible and are moving so quickly at all times, there's mostly empty space in between the particles. They're as far apart as they can be. And they can also move freely past one another. So all of these properties are unique to gases and different from liquids or solids. So in order to understand gases on the particle level, like if we could zoom in all the way and see either the atoms or the molecules of gas, we can describe it with something called the kinetic molecular theory, or the KMT for short. So the kinetic molecular theory is based on the idea that all matter is made up of tiny particles that are in constant motion. And so this kinetic molecular theory best describes gases. And specifically, it assumes something called an ideal gas. We're going to talk a little bit more about ideal gases when we talk about the ideal gas law. But an ideal gas is essentially an imaginary gas whose properties perfectly fit or align with all the assumptions that we're about to talk about that the kinetic molecular theory has. So they completely abide by the rules or the assumptions in the kinetic molecular theory. You'll notice in this photo that the big difference in an ideal versus a real gas is we're going to see that ideal gases, one of the components of the kinetic molecular theory is that there is no attraction between the particles. They're completely independent of one another, which we see in this picture. But here, however, real gases actually do have some some attractive forces between the particles, and so that's going to cause them to have some attraction, which is actually going to make their volume a little bit less than what the ideal gas law suggests. So, the assumptions of the kinetic molecular theory. The first, gas particles are extremely far from one another compared to their size. So that's what we said a minute ago of mostly, if we have a gas, the volume is mostly empty space. The particles are much, much smaller compared to the space that is between them. And so that means that essentially, if we are talking about a sample of gas, the mass of the gas particles themselves are pretty much negligible. Because again, when compared to all of the empty space, there's way more space than there is actual particles. Number two, gas particles are in constant rapid motion in completely random directions. This is because gases have very high kinetic energy. So kinetic energy is energy of motion. So the energy associated with anything that is moving. So gases are at the highest temperature when we're thinking about our three states of matter. So if they have high temperature, that means they have really high kinetic energy. So they're in constant rapid motion. Third, collisions between gas particles are what we call elastic. So a collision is exactly what it sounds like when two gas particles hit one another. An elastic collision is one where there is no overall net loss of kinetic energy. So in other words, we have two particles that are moving with a certain amount of energy, they hit one another, and then they continue moving with that exact same amount of energy. This is different from an inelastic collision where there would be some loss of kinetic energy. So you can think of an inelastic collision kind of like when you're playing pool and you hit that white ball and it's moving with lots of kinetic energy, but then it hits another pool ball and now it's moving way slower than it was before. Some of its energy is lost. This is different than what assumption 3 of the kinetic molecular theory is saying, and that gas particle collisions are elastic. So when they hit one another, there is no loss of energy. Assumption 4 is the one I talked about earlier when we referred to the photo. There's no net forces of attraction or repulsion between the gas particles. So what that means, if they're neither attracted to one another or pushed away or repulsed by one another, then the motion of each individual gas particle is going to be completely independent of the motion of all other particles. So they move completely independently of any of the particles around them. Finally, assumption number 5 is that the average kinetic energy of gas particles is dependent on temperature. Now, this makes a lot of sense when we know the fact that temperature itself is just a measure of average kinetic energy. So if temperature is just a measurement of average kinetic energy, then of course it's dependent on it. And so average kinetic energy is directly proportional to the temperature. So again, it makes sense if that's what it measures. So in other words, as the temperature goes up, the kinetic energy or the movement of the particles is also going to go up. Speaking of relationships, one thing going up and the other thing going up, or vice versa, there are two relationships that are going to be important for us to make sure that we know what they are when we're talking about gases, because we're going to be talking about relationships between different variables of gases. So the two relationships, and you've heard of them before, whether you believe it or not, you've definitely seen it in math class, and that's directly proportional and inversely proportional. So directly proportional literally means that as one variable increases, the other will increase. This would be the same vice versa. If one decreases, the other would also decrease. And if we're looking at this in a graph, it's going to look like the line here. See, as whatever is on the y-axis, or excuse me, whatever's on the x-axis, as it gets bigger and bigger and bigger, so does whatever is on the y-axis. So that's directly proportional. Inversely proportional is just the opposite. As one thing increases, the other will decrease, or vice versa. So as one goes down, the other goes up. So a graph is going to look like the one below. So as whatever is on, so B, for example, whatever's on the x-axis, as that goes up, we see that the y-axis is actually getting lower. So we need to recognize what a directly proportional relationship is and what an inversely proportional relationship is. So I mentioned that those relationships are going to be applied to the variables that affect gases. So there are 4 variables that affect the behavior of a gas and affect one another. The first is pressure. So by definition, pressure is the force exerted on an area. So gases exert a pressure when they collide with the walls of their container. So think about gases in a balloon. They have a pressure because they're hitting the sides of the inside of that balloon. Gas pressure is measured with a barometer. The units are a couple different ones. There are millimeters of mercury, which is most often written mm, Hg. That unit comes from when they actually used to use literal barometers made with mercury. And inside the barometer, the mercury would move from, this level maybe up to here. And so how much it moved would literally be measured in millimeters. So that's where that unit comes from. Pascals, atmospheres, and torr. Atmospheres is the most common unit that we use for pressure. The next variable is temperature. So we kind of mentioned that already in the kinetic molecular theory because the average kinetic energy is directly proportional to the temperature. So for gases, temperature is always, always, always going to be measured in Kelvin. I cannot stress this enough. When we are dealing with gases, you need to always convert the temperature to Kelvin. Now, the reason why. We're going to be doing lots of math with gases, and we need our temperature to always be a positive number. And the Kelvin scale goes to 0. That's absolute 0. It cannot be negative. So degrees Celsius can absolutely be negative. So that is why we always have to convert to Celsius whenever we are doing gas problems. So in order to do that, we are always just going to add 273. So whatever it is in degrees Celsius, we're going to add 273. And it's also important to know with temperature that at any given temperature, all gases have the exact same kinetic energy. So if I have a sample of oxygen gas at 200 Kelvin and a sample of nitrogen gas at 200 Kelvin, they have the exact same kinetic energy. The next variable is volume. So we already said that gases take on the volume of their container. So volume is the amount of space inside whatever container the gas is holding. So that volume can be measured in meters cubed, but the most common unit, of course, is liters. And finally, we have amount of the gas. And just like anything in chemistry, our most common way of reporting the amount is in moles. So this is the amount of particles. We do know that in 1 mole, there's 22.4 liters of any gas at STP. So that only applies at STP. And we can convert mass of a gas to moles using the molar mass, and we can convert volume to moles using the molar volume. Okay, so today we are going to talk about the different gas laws and how they relate different variables, the variables that we talked about last time, those 4 different variables: pressure, temperature, volume, and amount, and how we can use them to do calculations. So the first is called Boyle's Law. Now, I'll go ahead and tell you that I will never ask you a test question that says, which one of these is Boyle's Law? I don't really care that you know that some scientist whose last name was Boyle was the one who determined this specific relationship. However, what you do need to know is that pressure and volume are inversely proportional. So inversely proportional, remember, means that as one goes up, the other one goes down. So think about a balloon. If I squeeze that balloon, I'm making its volume smaller. But inside, I am increasing the pressure of the balloon. Because if I'm decreasing the volume, then I'm going to cause the particles to collide more and more and more with the sides of the container, which is going to increase the pressure. That's why if you squeeze the balloon hard enough and long enough, eventually it will pop. So our formula for Boyle's Law is P1 times V1 equals P2 times V2. And if we were to graph Boyle's Law, we're going to see this nice inversely proportional graph, because as we see, as the pressure goes down, as the pressure is going up, the volume is going down. So they are inversely proportional. The formula is P1V1 equals P2V2. Charles' law relates temperature and volume, and it finds that temperature and volume are directly proportional. And we can think of this like a hot air balloon. So before it turns on, the balloon is not blown up. But then when they turn the fire on, that increase in temperature causes the balloon to expand, because as the temperature goes up, the volume goes up. That is directly proportional. And so the formula is V1 over T1 equals V2 over T2. And I didn't mention this on the last slide, but what we mean by these ones and twos is that we mean if we have a gas, so like if we look at this picture, if we have a gas at a certain temperature and it takes up a certain volume, that would be T1 and V1, and then we change its temperature, so that would be T2, we can then calculate its new volume, which is V2. So this just means the first set of conditions and then the second set of conditions. That's what we mean by 1 and 2. And again, if we graph this, we see it's a nice directly proportional relationship. Gay-Lussac's law determined that temperature and pressure are directly proportional. So again, pressure comes from the particles colliding with the sides of their container. So if we increase the temperature, then we're going to increase the number of collisions because the particles are going to be moving more and faster. And so that's going to increase the pressure. So again, these are directly proportional. So we see this nice directly proportional graph. And the formula is P1 over T1 equals P2 over T2. Finally, we have Avogadro's law. And Avogadro determined that for a gas at a constant pressure and temperature, volume and moles are directly proportional. So this time, as the number of moles go up, the volume is going to go up. We see this nice directly proportional graph. And this one makes very intuitive sense because if we have more gas, we're going to take up more space. And the formula for this one is V1 over N1 equals V2 over N2. Now, I will tell you that this variable, this number of moles, is going to be something that changes the least. Typically, that's going to be one that stays constant. So this particular formula is probably going to be used the least. So here you have this in your notes, but this is just a nice summary of all 4 of those gas laws with what their formula is, what a graph of them would look like, and if they are inverse or directly proportional. So it's easy to see here, and for you to remember, pressure and volume are the only ones that are inversely proportional. The rest are direct. So when we are working gas law problems, if you want to, and these first ones in your notes, I'm going to have us do the chart like this. This chart can help us to solve these problems because they can help us kind of put things where they belong. So initial is the same thing as 1. So like when it says P1, V1, so initial would be that 1. And then final would be like the P2, V2. So that would be 2. This effect row is just for you to kind of think conceptually. If one's going up, what's going to happen to the other one? Any variables that stay the exact same from the initial to the final, or from 1 to 2, we can just totally ignore those because those are going to get canceled out. So let's look at an example. We have 2.5 liters of a gas at 3 atmospheres of pressure. It is condensed, that means its volume's lowered, to 0.5 liters of gas. What is the new pressure? So if you notice, there's nothing about changing temperature, so we can ignore that. And there's nothing about changing the amount, so we're going to ignore that. So our only 2 variables that are changing here are pressure and volume. So we have the initial pressure, which is 3 atmospheres. We are being asked for the new pressure, so this is what we do not know. Our initial volume is 2.5 liters, and then our final, or our second volume, is 0.5 liters. Now, if we think about this conceptually, what's happening to our volume? Our volume is going down. Well, we know that these are directly proportional, or inversely proportional. So the volume goes down, I'm going to expect that my pressure goes up. Now I'm going to actually solve the problem, and I'm going to do so by plugging it in to our formula, P1V1 equals P2V2. So you can see here that when we plug that in, we have 3 atmospheres times 2.5 liters equals P2 is our unknown, that's the one that we did not know, times 0.5, which is the new volume. So in order to solve for P2, we got to divide both sides by 0.5, and we get that our new volume is 15 atmospheres. Now look, we can kind of use this as a check. We expected that because the volume went down, the pressure would go up, and in fact, it did. Now you'll notice over here that what I did is I wrote down all of the gas laws together. And if you look at your reference sheet, you are given this, except yours does not include in. And that's because it's like I said before, most often in is kept the same. And so there's no reason to include it because it just gets canceled out. But because all of them are combined on your reference table, so on your equation sheet, what you have to do is just ignore whichever one you're not using in the moment. So for this one, we weren't using temperature. And so that's how we got the formula, just P1V1 equals P2V2. All right, let's look at this next one. 55 liters of oxygen gas at 300 Kelvin is heated to 500. What's the new volume? So for this one, we are not changing the pressure or the amount. So we're just focused on volume and temperature. And again, on your equation sheet, you are given this entire equation. But because temperature and volume are all we're focused on, pressure isn't changing, I get to just ignore that. And so the equation I'm going to use is V1 over T1 equals V2 over T2. I just left out that pressure variable since it is not changing. All right, so go ahead, take a second, pause video, and try to fill in the variables in both the chart, predict the effect, and then find the new volume. Hopefully, when you did that, you got an answer of 91.7 liters. So we plugged in 55 liters for V1. We don't know V2, that's my unknown. We had 300 Kelvin for T1 and 500 for T2. So to solve for V2, I had to multiply both sides by 500. And then, so essentially I cross multiplied here. So multiplied by 500 and then divided by 300. And I get 91.7. Now, the temperature went up, so I anticipated that my volume should go up, which it did. All right, next question. A gas at 42 degrees Celsius is cooled to 11.2 liters. Remember, liters is volume at 22 degrees Celsius. What is the initial volume? So for this one, I am not changing pressure. I'm not changing amount, so I'm just looking at temperature and volume. One more reminder, This time my temperature is given in Celsius, so I have to convert both of them to Kelvin by adding 273. So take a minute, pause video, fill in the parts of the chart, and then fill in the formula and solve for the initial volume. So hopefully when you did that, you got a new volume of 10.5 liters. So I plugged in 11.2 for V1. I did not know V2, that was my unknown. I had 315 Kelvin for T1 and 295 Kelvin for T2. So I'm going to cross multiply, and I get 295 times 11.2 equals V2 times 315. So I have to divide both sides by 315, and I get 10.5 liters. So my temperature went down here, and so I expected my volume to go down, and it did. Now, sometimes we can change 3 variables at the same time. And if that's the case, we're going to use the entire equation that's given on your equation sheet rather than ignoring one of them. But everything else is going to work exactly the same. Now again, if you want to use the chart, you can. Notice I did take away the effect row for this one because when you're changing 3 variables instead of 2, it's difficult to know which one's going to have the greater effect. So you wouldn't be expected to know exactly without doing the math what the expected change is. So again, we are going to do this exactly the same. It's just this time we're going to have 5 total things to plug in with 1 missing. So here we're given temperature, pressure, and volume. And then we're lowering the temperature. This is our new volume. My question is, what is the new pressure? So again, I'm not changing the amount. So as I told you guys, that one's pretty much never going to change. And I am changing pressure, volume, and temperature, however. So pause the video for a second. Remember, this time you're using the entire equation. Plug in your variables to the chart, plug them into the equation, and solve for the unknown, which is P2. When you did that, hopefully you got 1.88 atmospheres. So we plugged in everything that we knew. 1.3 atmospheres was the initial pressure. The final pressure, or P2, was my unknown. Initial volume was 15. Final volume was 10. Initial temperature was 293 because remember we have to convert to Kelvin. Final temperature was 283 Kelvin. We plugged in everything we knew. We solved for P2 and we get 1.88 atmospheres. One more practice problem with all 3 combined. We have temperature, pressure. We are lowering to a new temperature, a new pressure, and volume. So I am solving for the original volume, which would be V1. So again, amount is not changing. So we are going to plug in what we know about the other 3 variables, and we are going to solve for our unknown, which in this case is V1. So pause the video for a second. Try to work this out on your own. And when you worked it out, you should have gotten that the volume, the new volume, or excuse me, the initial volume was 22.5 liters. P1 was 5.3, P2 was 4. V1 was our unknown, V2 was 27.5. Temperatures were 328 to 303. We solved for V1 and got 22.5 liters. One other gas law that I want to talk about really quick is one called Dalton's law of partial pressure. This one is extremely easy. It just states that the total pressure exerted by a mixture of non-reactive gases, so meaning when we combine them together, there's no chemical reaction, they just are now multiple types of gases in one sample. The pressure of all those gases is just going to equal the sum of the pressure of the individual gases. So the total pressure, once we add them together, is just equal to the pressure of each of them individually added together. So again, super simple. In this example here, we had a pressure of hydrogen gas by itself of 2.9. Then we had a pressure of helium gas by itself of 7.2. When we put both of them together, we literally just add their pressures, meant to say 2.9 plus 7.2 equals 10.1. That's it. Super easy. And that's all for today. All right, welcome back. This is our last lesson in gas laws, and today we are focusing on the ideal gas law. Now, the ideal gas law formula is PV equals nRT. This leads some people to call it PIVNRT. So sometimes you'll ask somebody, well, what do we have to use to calculate this or to do this problem? PIVNRT. And that's just the ideal gas law. PV equals nRT. So it relates all four of our variables at the same time: pressure, volume, amount, which is in moles, and temperature. The ideal gas law works for any gas, and where it came from is the fact that whenever pressure times volume is divided by amount times temperature, you are always going to get this constant R. So R is our ideal gas constant. That number never changes. The only way it will change is if it's expressed in a different unit, but it is still the same amount, okay? So this is our formula. This is, of course, on your equation sheet. PV equals nRT. What do each of those stand for? So PV equals nRT. P is, of course, pressure. Pressure can be in atmospheres, kilopascals, millimeters mercury, or torr. Volume is in liters, so V is volume. Something to remember, sometimes we might be given volume in milliliters. So to convert milliliters to liters, we would just divide by 1,000. So if we were told that we had 250 milliliters of a gas, and we wanted to plug that into the ideal gas law, we have to convert it to liters. So that's going to be 0.25 liters. So I'm just moving the decimal over 3 places, dividing by 1,000. N is the amount, or moles. Now, this is going to take some of our prior knowledge. If our problem gives us grams, there is nowhere in this ideal gas law to plug in grams. So we have to convert grams to moles. But that's easy peasy. We've been doing that forever now. T is, of course, temperature, and just like I told you before, we are always going to convert that to Kelvin. So if it's degrees Celsius, we add 273. And then R is that ideal gas constant that I mentioned to you before. Which R we use depends on the units of pressure. We have different R's based on which unit the pressure is in. The other three do not change. It's always liters, moles, and Kelvin. So pressure is the only one that varies. But you will see on your equation sheet that you are given 3 different gas constants. And notice that the only thing that's different about them is the unit of pressure. So if you're working a problem and the pressure is in atmospheres, you're going to choose this R value. If the pressure is in millimeter mercury, you're going to choose this R value. If it's in kilopascals, you're going to choose this R value. Now, notice down here that 760 millimeters mercury is equal to 760 torr. Those are the exact same. So if you were to ever be given torr, you would just use the 62.4 because it's the same as millimeters of mercury. So let's look at an example using the ideal gas law. So one thing that students get a little confused about at first is they're like, okay, when do I use the ideal gas law, PV equals nRT, compared to our other gas laws, which was P1 V1 over T1 equals P2 V2 over T2. And then one of those variables might be ignored. How do you know which one to use? Well, when we were using these gas laws previously, you notice that the conditions are changing. So in all of those problems, it said something like, we had an initial volume of blank and a temperature of this. We changed the volume to this. What's the new temperature? So we always had changing conditions where we needed to have a 1 and a 2, or an initial and a final. Notice for PV equals nRT, there are no 1s or 2s, so there are no changing conditions. So you will only be given one number for each variable, not two. So we look here, we have a 2.5 mole sample of carbon monoxide. Its volume is 20.3 liters, and this is at 31 degrees Celsius. Now, something I want to point out really quickly is the ideal gas law is used at any point in time. So if we have to calculate volume or go to moles or anything like that, we can use the ideal gas law at any time. So this works even when we are not at STP. All right, so look at what we are given. We are given the volume is 20 liters. The number of moles is 2.5. The temperature was 31 degrees Kelvin, so I got to add 31 degrees Celsius, so I got to add 273, which is 304 Kelvin. And then I figure out which R to use based on the fact of which pressure. Now for this one, we were not given a pressure. So if we're solving for pressure, you can really just pick any R, and then your pressure unit is whichever pressure unit is in the R value that you picked. Most of the time, and I believe on your practice set, I told you if you're solving for pressure, just use atmospheres, okay? So if we're going to solve for pressure in atmospheres, then we have to use that top R value because that's the one that's in atmospheres. Now, P is what we're solving for. So we have PV equals nRT. We're going to plug in our variables and solve for pressure. So we have moles times R times temperature. And that is going to be divided by 20, which was our volume. And we get 3.1 atmospheres. Again, that pressure unit we get straight from the unit of R. Now, just so you're aware, remember how we learned 1 mole is 22.4 liters at STP. That is not some random number. That actually is calculated using the ideal gas law, because STP is 1 atmosphere and 273 Kelvin. So if we use the ideal gas law, we plug in 1 atmosphere, 1 mole, 0.0821 is the R value that's in atmospheres, times 273, which is standard temperature. When we solve for volume, guess what we get? 22.4 liters. So that 22.4 liters was not random. It is just exactly the amount, the volume that's in 1 mole at 273 Kelvin in 1 atmosphere. And because that's standard, we kind of just said, okay, a lot of your calculations are going to be done for problems that are at standard temperature and pressure, so let's just have that shortcut. But now if we are not at STP, we cannot use that 1 mole is 22.4 liters, so don't forget that. All right, so let's do some practice. Sample of gas has a volume of 12.8 liters at a temperature of 20 degrees Celsius and a pressure of 105 kPa. How many moles are in the sample? So this time we are looking for N. So first thing we want to do is we want to write down everything that we are given, if that helps you kind of keep track. So we knew the pressure, we knew the volume, we're looking for moles. We pick the R value based on the units of pressure. The units of pressure here were kPa, so that's why we use 8.314. And then temperature, we always convert to Kelvin. So PV equals nRT, and so we're going to plug in 105 times 12.8 equals N times 8.314 times 298. So in order to solve for N, we're going to do 105 times 12.8 divided by 8.314 divided by 298, and we get 0.54 moles. Now notice over here what I wrote. Sometimes students mistype in their calculator. So two ways that you could insert this into your calculator: 105 times 12.8 divided by, if you want to do the multiplication on the bottom at once, you need to put it in parentheses. The other way you can do it is say 105 times 12.8 divided by 8.314 and then just click divided by 298 again. What you cannot do is plug in 105 and then click times 12.8, then click your divided by button, 8.314, and then click your times button, 298, because that is going to divide by 8.314 first and then multiply rather than doing all of that at once. So just keep that in mind and check to see if that's what you did. If you're checking your work at some point and you plugged everything in right and your answer doesn't match, that might be what happened. All right. 28.4 gram sample of carbon dioxide gas at 32.4 degrees Celsius has a volume of 16.7 liters. What pressure does the gas exert? So now, this time we are given grams, temperature, volume. We're looking for pressure. We always know R, we just have to pick the right one. In this case, we're solving for pressure, so we can pick whichever one we want. I'm going to use the first one. But now, we have one problem. PV equals nRT. There is no variable for grams. I mentioned this before. If this happens, if we're given grams, then we have to convert those grams to moles. But we have been doing that since Unit 5. If I have 28.4 grams, then I just have to figure out how many grams are in 1 mole, which I do with the periodic table. Carbon is 12, oxygen 16. 12 plus 16 plus 16 is 44 grams. So once you convert that to moles, try to plug everything in to the ideal gas law and solve for pressure. Maybe pause the video for a minute, do it on your own. When you do, first of all, when you converted 28.4 grams to moles, you should have gotten 0.645 moles. So now we have volume, moles, R value, and temperature. We're going to plug all of those in and solve for pressure, and we get 0.968 atmospheres. One more practice problem. What is the volume of 35 grams of nitrogen gas at 25 degrees and 1.2 atmospheres? Excuse me, 1.12 atmospheres. Take a minute, pause the video. Okay, hopefully, first thing you noticed was that you have 35 grams. So you're going to have to convert that to moles. So if we've got 35 grams of nitrogen gas, nitrogen is diatomic, so it's N2. So 1 mole of nitrogen is 28 grams. That gives me 1.25 moles. So now I have everything but volume. The R value is based on atmospheres this time, so we're picking that top R value. And we plug in everything we know, solve for our unknown, which was volume, and that is 27.3 liters. All right, so guys, just like everything this unit, it's just lots and lots of practice. So at this point, you just need to do lots of practice problems, and I know that you'll get the hang of it.